Hello everyone, I'm Fazeleh. This was my introduction. I'm here to present our work, PTNT, Process Tensor Network Tomography. This work is for modeling the realistic physical noises using the experimental data. And the idea behind that is using the process tensor tomography and the process tensors and using the, some runtime design that are not going to disturb the workflow. I know that is a little bit kind of like complicated, but at the end you can understand what is happening. The output of this project is going to be both of the scientific result and also is going to be an open source software. I mentioned that we are going to model noises, but what is all of these noises about? What are them? When we are talking about the classic computers, every line of the code that you are running, every time are going to give you the exact same result. When I'm talking about quantum computers, you really expect to see the same, behavior. Because in ideal world, when you are trying to perform and execute a, operation on quantum hardwares, basically we really expect to see an individual, a repeatable, and a predictable result. But unfortunately, quantum hardwares are not like this, and they are extremely fragile. And they are making noises and mistakes in 3 different ways. So we can just divide all of these noises in 3 different categories. First of all, it's environmental memory, and the idea behind that is because qubits are not isolated. And for example, if one error or noise happening in the in any time step, it can be a delayed result of one operation that happened a few steps earlier. So we can say that system basically can remember its past. So every time, every operation is kind of like related to a few steps earlier. And the other one is control drift. Qubits are controlled using the microwave pulses, and the electronics that are generating these pulses are really fragile, and basically they are going to have a little bit fluctuation over the time. So if you are running several times an operation, you can see that they are basically getting a little bit different physical result because of that fluctuation that I mentioned. The other thing is crosstalk or spillage. This is really common, and it's because qubits are saved tightly inside of the silicon chips, and if you are throwing a strong signal to one qubit, you can see that for running an operation, definitely you can see that they might accidentally spill over some of these pulses to their surrounding qubits and disturb them. So every time that I'm talking about crosstalk and thinking about that, I'm feeling like they're kind of like qubits are talking to each other, so it's happened most often. There are a lot of softwares there that they wanted to characterize the system and model the quantum hardwares, but unfortunately they were just considering all of these complex noises as a simple background noise. Our project came and mentioned that we should stop ignoring all of these complex noises and consider them as a actual noises that we can see in the environment and in each of noisy controls that we have. But the question is how we are modeling the noises. This is really a complex and challenging question because basically we are living in dark. Because the only things that we know is the output file. Because we are, for example, running a bunch of sequences, and we are generating some output measurement of 0 and 1 at the end of each circuit. So we don't know anything about anything else. For example, everything else is in the hidden part, and all of those timeline memory that I mentioned, control drifts, spillage, everything that is happening in behind scenes that we don't have any idea about them. And there is another challenging things which we are not able to measure or system when it's running. So this is another challenge that we can just understand what is happening in the middle. We need to extract the comprehensive mathematical model out of this hidden layer or hidden steps. We need some mathematical model that basically can consider both of the background noises and all of those noisy imperfect controls that there are in our quantum hardwares. As you can see, we are just dealing with an inverse problem because all of the standard physical simulation, you have the model and you're just throwing some inputs into them and you're getting the output, right? But we have millions of imperfect controls and we have the experimental data, and we really want to infer the mathematical model that is generating those experimental data. The next question is why we should care about this, because this is actually a really difficult problem and people are just trying to solve that, and this is kind of has a huge impact. So we saw that this is not only impacting the quantum computing, also it's just impacting the industry and the hardware and system teams as well. In the quantum computing, I'm not sure if you heard about the quantum error correction. This is really a hot topic that people are really caring about them. In this part, if you want to fix any noises, the decoder needs to know what the error is, because they are not able to just go around and just randomly try to fix some noises that they don't know where it's happening. For example, if it's a noise is happening in a gate or a control, how they can just find which control is there to fix that. And also for calibration, you really need to know where the noise is happening, because different noise sources actually requires the different fixes. And even for having the better compilers, for example, you really need to know the source and the reason of the noise, because, for example, you can change a gate to a better gate to avoid all of those bad areas. The other impacts that our software can have is just in the hardware and system teams, because it's going to help for richer diagnostics. Our software is going to act as a medical, scanners. Is going to say that where the noise is happening and what the noise is. Then the engineers in the hardware companies know what is in front of them and they can deal with them. And also, unfortunately, quantum computers doesn't have the same structure. So, for example, the noises and the structure and the characterization of each quantum hardware is different with the other one. So every time that the engineers want to characterize their system, they had to coding up everything from the scratch. But we are offering a general software that we are just offering them to give us some input, the raw input data from their system, and then we are kindly give them the model and characterize their quantum hardwares. If you really want to see where pretentious is among the existing models, you have to ask yourself two questions. First is, does the environment have memory? If the environment has any memory, we are calling that as non-Markovianity. And are the controls perfect? This table is the table that does make sense for me when I was just reading the literature. So I just wanted to characterize all of the methods that is really in this field, famous to introduce to you. If there is no memory and there is a perfect controls, it's going to call a standard tomography, but it is not realistic, right? Because we have noises, definitely. One of the good methods that is out there is get-set tomography or GST. They are not considering any memory and they are trying to learn the imperfect controls. This method is really perfect to finding the noisy controls, but unfortunately, this is actually Markovian and it's not non-Markovian. In contrast, the standard process tensor tomography came and just did the opposite things. It considered that the system is non-Markovian. They consider some memory in their system, and they consider all of the gates and controls are perfect. So we have some gap here as well. We can't, point any noises in the control, but we can just like consider and learn all of the background noises perfectly fine in this method. PT&T, our method, came and just like tried to fix all of the gaps between these two great methods. We have the memory. We consider that our systems has memory, which has noises, and also we are considering all of the controls are imperfect. So we can imagine that for them, there might be some noises in the control that we have to find and characterize them. I bring this table as well. As you can see, PTT and GSD has some blind spots, which PTT is just like filling all of those blind spots. For example, our method is learning the control jointly and models the process memory, and it also models the control correlation and the spillage, which both of the GSD and PTT is not covering them. So PTT and GSD is not considering the crosstalk noises or the spillage, which, as I mentioned, they are really common. And if you are not considering that and trying to characterize your system, basically you are not characterizing your quantum hardware accurately. As PTT is trying to cover everything, it's going to be really expensive and it's going to add a computational burden. GSD has the lower computational burden because it's just like trying to consider the imperfection on controls, and there is no any noises in the memory, so you even don't need to have maybe HPC systems to characterize your system for the GSD. But a standard PTT, when they are considering the noise memory, they have to use some process tensors that if they want to work with larger systems, they have to use some HPC to improve their computational issues that they are facing too. PTT is acting as an AI style differentiation inverse problem. This slide is actual engine of our problem. We have 3 steps. The first step, like all of the AI problems, we are trying to guess. In the second step, we are just like trying to do some reality check, the loss function, and at the end, we are just trying to fix the model by doing a backward pass and update. For guessing, we are guessing a model. The model that we are just like trying to offer that to the user as the noise model. So we are considering a process tensor. In the next slide, I'm going to tell you why we are considering our mathematical method as a process tensor. Also, we are going to make some testers. Testers are those circuits that we are trying to run over the quantum hardwares. We are trying to raise 6,000 at least testers using a lot of gates and over the time. So it's kind of like a process tensor as well. Then we are combining these two, the model that we have and our testers, by contracting them together, and we are just like finding the prediction. For example, I'm getting like 40% of the time we are getting the output measurement as 0. Then we are going to do some reality check. We are running all of those testers in actual hardware. I might get, for example, 85%, 0. So in this case, I'm really wrong. Then I have to do the backward pass and update our cases. We are doing the automatic differentiation runs backward through the tensor network contraction, which is our gradients. And then we are doing the optimizer to update the parameters. Before going further, I'm going to tell you that why I considered and guessed my method as a process tensor. We need some mathematical model, but we don't need to, and we don't want to work with any mathematical model. We want to choose a mathematical method that can fit in the computer firstly, and also we want a method that it can show the physics and the physics behind the problem. If we want, some people are just like raising that we can work with quantum channels. This is working if we are working for GSD because we are not considering the memory and memory noises. Because quantum channels, basically, they are getting the input and throwing out the output, and it's not considering the timeline or any memory behind that. So we are using the process tensor because it's a multi-time object, which is really perfect for our method, and also we can apply some mods on process tensor, and we can ignore the long-range noises. Because, for example, qubit 0 in timeline, for example, t, can't affect or have a crosstalk with qubit, for example, 20. So we have to ignore them to reduce some computations. You might think that we have AI, so why we need HPC? But because all of you are expert, definitely you know that why we need HPC for this problem. The dominated time cost and the dominated memory cost is really related with the system size. In this case, the system size is really related to the number of the qubit and the number of the timetable. When I started working with this, it was really funny for me because I was thinking 4 qubit and 4 time step is a small system. So I started to running this, a naive process tensor with 4 qubit and 4 time step. But my memory was just like explode. So I couldn't run that and was just like, what is going on? So I saw that using 4 qubit and 4 time step is going to give me 137 billions of data, which if I'm using the complex 64 data or complex 128, it needs 1 to 2 terabytes of RAM. And the bad news is I'm not even starting the math. This one was the data that I just was putting in the system. So if I want to do the math, even in the first step of the AI guessing, if I want to do this contraction in the first step, it's going to have a lot of intermediate steps and everything. So it's going to kill my memory. So you can survive, your GPU. So definitely you can just like run a dense single process tensor for this problem. You have to have a lot of trick for doing this. This problem was a little bit different from the other, big data problem or AI problem that I have seen because every part of this problem that I touched, it has one issue. Everything was not really related. The physics behind everything was just like affecting the data, affecting how I'm just like dealing with them. So I had to deal with the concept. I had to deal with AI. I had to deal with the HPC. So it was quite complex, and the workflow of the whole software but is easy. I was getting some input, and the input, I'm going to explain in a further slides, it was not a simple input, so I had to make a compiler to make the inputs canonical object, and then I had another compiler, which was combined runtime, to find a different path to run my calculation based on the different inputs and different physics that I was getting. And then in each of paths, I was doing the training and reporting the model. When I wanted to implement this software, I realized that the audience or the users of this software is not only the academic, or it's not only the people and the engineers in the quantum hardware companies. It might be some, curious person. It can be a PhD student. It can be some, academic level that they just want to check how this workflow is working. So they don't have a real input. They don't have a real data, raw data from actual quantum hardwares. Or there is some, companies that we were just like talking to them, and they were just like providing us some actual, quantum hardware, and they are really wants to see which part of their system there are noises to just like fix and improve their system. So if the data is a raw data, or is coming from different quantum computers, they are different. And also, if someone like me, they don't have any actual data, they want to simulate data and just like run the program and see how it goes, right? So I'm getting all of those data, and I'm just like making them as just like a stable public schema, and trying to run them. But when I wanted to just like implement the training part, I find another issue. The physics behind all of the gates are really different, because a lot of problems and a lot of people are just interested, or even the computer quantum hardware, they just want to work with local gates. Local gates means that there are some gates that they're just like The best way to explain that is just like imagine that you have a grid, and the row of this grid is going to be the qubits, and all of the columns is going to be a timetable. Each dot inside of this grid is going to be a gate. If each gate is just like isolated for that grid, it's going to be a local, gates. But sometimes we have 2 qubits gates, or we have 3 qubits gates, which is kind of like common between 2 qubits, like X0 or other, gates that are there, and we have to deal with them differently. So in terms of, data structure and not overkilling our, resources that we had, I had 2 different paths for dealing with these 2, type of gates. After I had public schema, I had a local fast path, and I had a generic non-local path. When I wanted to implement in this stage, I find another issue. People in this area really love Python, and I really love C++. So I had to deal with Python, and I realized that Python really loves dictionaries. GPU hate dictionaries, right? So if you want to get a good result from GPU, you have to make GPU happy. So you have to provide some data structure that GPU really loves, then it makes something for you, right? So instead of creating some dictionaries that no one likes except Python, we were just like trying to make a dense, large grid, right? I was creating 5D arrays to calculate all of the, to put all of the, data for local fastpath. I mentioned that a few slides earlier that we had 6,000 circuits, right? If we want just like to do all of those contractions, it should be a for loop, right? So we have to send all of this data. Contraction is going to be happen in the GPU, and then we have to get back data. GPU is fast, but the connection between this, CPU and GPU was killing, the timeline for me. And when I was profiling it, it was the most disaster things that I could see. So in this case, when I was making that as a 5D array, I was putting one of the, dimensions as a circuit. So the first dimension is 6,000 circuits, and the second one is qubits in each of these, circuits. And the time step, 2 by 2. This 2 by 2 is just like a dimension of each of these gates in the local gate, which is really fixed. This one was the neatest, dense array that we had. But when I was dealing with the non-local one, this was another disaster that I was facing, because no one loves to do the non-local. When I was doing a research, I saw that no one is just like trying to implement that, because they are just like, we are doing whatever that we can do. We are doing our best. We can just like, can't work and deal with non-local, gates. But we are smart, and we can deal with them, right? So I was just like, this is my next challenge, and I have to deal with that. So I was just like trying to see what is the specification and what is, the feature of these non-local gates. Non-local gates is not just a, computer science problem. That there is some data, and you have just like to deal with that. Unfortunately, everything in this area is just like real. We have real gates there, but we know there is some, noises. This one was a really issue, because we are trying to model a, mathematical model of the noise, but the hardware actually is there. If we have some gates in this model, they should be in specific places. So we are going to have an ugliest, dictionary that you could imagine, that it has some events based. It's going to tell you that each gate is going to be and allowed to be in which part. For example, which qubit can have this, gates, which time step is going to consider that. And also in the non-local gate or those, circuits, we don't have the 2 by 2, fixed gates, because some of them are 2 qubits, some of them are 2 qubits, and they had a different, sizes. The naive things that I was thinking about was just like, okay, I have this local fastpath, which is really fast. Instead of 2 by 2 that I mentioned in here, I can just like find the worst case scenario, which is 3 by 3, for example, the 3 qubit gates, and I'm just like doing padding for the rest of the qubits, right? And everything is easy, and I'm genius, and I can just like running it in 1 hour. But it has 2 issues. My memory was killed again, and my laptop, I was not able to work with it anymore. And the supercomputer was hanging, and everything was really bad. So I was just like trying to fix that, and then I realized that because of those event-based that we have, we are not able to get an accurate result because we were duplicating each gate. For example, if it was a gate between 2 qubits, actually we were just like copying it 2 times. So we were not able to use this data structure for that. So I was just like trying to have a different data structure. I was using different kernels and packaging or batching all of these kernels over the timetables. So I had 1 qubit kernels, 2 qubit kernels, and 3 qubit kernels. And we never have 4 qubits gates. They does not exist. And easily, I was able to have a 3D arrays, and padding them was just like really easy, and it was not killing the memory. So easily, we could just like compile the tables with these kernels and send them to the device to do the calculation for us. We have to keep this both of the local fast pass and the generic compiled event pass because each of them has different specification. And yes, I can calculate the local fastpass using the generic compiled event pass, but we are overkilling the resources. Local fastpass is good for throughput and device regularity, and generic one is really cool for correctness and generality for non-local workloads. All of the CLI and the canonicalization and bucket selection and checkpointing and reporting the model is going to be in the host, and most of the heavy lifting like the compile drawer or test and lookup, probability evaluation, tensor network contraction, and autodiff gradients is on GPU. This tensor network contraction is just like 2 words, but it is not acting like 2 words. It just like took months of me. It is just like something that is just like generating paths. It is generating, an intermediate path, and from nowhere it's trying to explode your, memory. So you can't use the, the packages easily that they are there, and maybe you have to most of the time do that manually. It's more, reliable from my side. And also we have MPI for optional or reduce and optimizer setup. This problem, as I mentioned, that it has 2 different outputs. It's going to have the scientific output, and another output is going to be a software, right? So we have to consider both sides. I never had experience of writing any software, so it was just like a little bit challenging again for me because, for example, running or dealing with some of the packages was just like making a lot of difference and or speed. And also, again, this was not only a big data problem. Everything was just like has meaning there in the quantum physics, I realized. For example, if user is going to give you 2 by 2 matrix for representation matrix for each of the gate, we can't just like accept that as it is because maybe this 2 by 2 is a PTM or coin matrix or super operation, representation. So I had to deal with all of this, representation, and our software is going to, consider in a general way, and every representation that there is out there for all of the gates, in this software is just like can deal with them. Our software is not finished. It is really good in terms of dense probability evaluation. At the moment, tensor network contraction is really perfect. And we have the autodiff gradients and optimization setup is on GPU. But for non-local paths, because lately, I was just like implement that, I still need to work on the optimization part to make it perfect and ready to launch. The next HPC milestone is push more of the generic compiled event paths into a native numeric contraction backend, and all of this is for the non-local one. The second one, the reduced compatibility-oriented tester materialization. I did this when I came to this, event. Make the irregular non-local paths as device-friendly as the dense local paths, and turn the architectural GPU readiness into the consistent time to solution wins. This is the result because I told you that, to be honest, I'm still working on the optimization for the non-local. I haven't brought any result for the non-local to you. So this is for the local one. And when we're just like comparing the PTNT with the PTT process tensor tomography, we were getting the more accurate result compared to the current result, which is understandable because we are going to consider the actual noises in the system. We are not ignoring any part. And also we could get 13 to 12 times GPU speed up as well. I have to tell you that something in this problem that I'm working with, speed up is one point, which is really great, and also the limitation is another point. The last application that I saw that they could work with the size of 18. And 18 means if you are multiplying the number of the qubits and the number of the time step, it should be 18. They couldn't arrange that to get something more than that. But so far, all of the testing which I'm trying to optimize and doing everything that I'm working with, it at the moment is 30, which I'm really proud of that. I really want you to get some takeaways, like real quantum hardware is noisy in ways that simple Markovian model miss. PTNT tackles the right scientific problem. It learns the multi-time process noise and imperfect controls together. The hard part is computational. It's repeated tensor network contraction. It was really difficult. Large data set and irregular runtime structure. The software contribution is a clear AI and HPC workflow. We have one public schema, 2 runtime layout, batch optimization, and a path towards stronger GPU native execution. PTNT is a case study in how quantum characterization, scientific machine learning, and HPC software design must work together. My presentation was until here, but my presentation is done. But okay, I came to the tutorial, and I'm not sure if you were all in the tutorial or not. I was in an AI tutorial, and the time that we were just like trying to make and generate a new image using the diffusion, I was all the time thinking about my control drift. So I was just like trying to apply the diffusion during these 2 days on control drift, and I got a good result. So I just want to share that with you as well. Can you remember the control drift that I mentioned? Are you listening? Okay, the control drift. We are controlling the qubits using the microwave pulses, and as I mentioned that the electronics that is generating these pulses is going to be fluctuating over the time. Okay, so we are getting a different physical result if you are running one operation several times because of that fluctuation. This one was the control drift. One of this drift formula is just like the pink noise, which we are giving each of this circuit. We had 6,000 circuit is going to receive a latent angle, and then we are just like rotating in the RX, we are going to have RX rotation for that. But this random number is not a random, okay? Because if it's a random, it's going to be Markovian, right? We are not considering the memory. So we are going to check that as a drifting randomness. I'm not sure if it's the right term, random, and drifting randomness, but it's worked for me. I hope it's working for you as well. So I'm pretty sure you couldn't get what I'm talking about, so I was just like bringing the algorithm in here. For the ping noise, I was hard coding that in the software before. When I'm talking about hard coding, I'm not telling that I was putting some number as a noise there. I was just like hard coding the meaning of the ping noise there, so the drifting. But it was not actually related to the hardware. I was thinking, yes, we are going to have some drifting noise, but it should be really connected to the hardware, right? In this term, it's going to be more accurate. So I was just like trying to do that. The hard-coded baseline was just like we had a white noise. Yes, in this quantum physics, they are just like coloring the noises based on, I think, something. White noise means actually random number. It's kind of like dicing a roll. So you are giving a random number, and then your cumulative sum, because you want to add memory to that. Otherwise, it's going to be Markovian. So for adding it non-Markovianity, you are just like cumulative sum to keep running total and make it related to what happened earlier, right? And then you have to normalize and scaling it, because you don't want to be more than 1, and you don't want to exceed the maximum noise that you can just like achieve. And then we are binding that to each of the gates and circuits, right? So this one was the ping noise that we were hard coding it. Again, it is not hard coding, meaning that we are just like putting numbers there. It's just like the definition of the ping noise. This hard coded was working perfectly fine because I was putting a seed, so it was just like reproducible, and it has issue, as I mentioned, because it's not related to the hardware. And I haven't seen no one do that, because everyone was just like using that hard-coded one. So I was just like thinking diffusion is going to be really perfect for that. So I was generating a sequence of errors, which is going to be from 1 to n time, by sampling from a probability distribution that our neural network is going to learn. This is really safe because we are not changing any tensor network, and we are just like changing this latent angle that I mentioned. So the quantum mechanics are the same, so I'm not destroying anything. This is the algorithm. If you were in the tutorial, you can remember that the algorithm is exactly like the one that we were just like for generating the image. We are going to start with real or synthetic drift traces. Then we are going to add random Gaussian noise to them step by step. And then we are training denoising a model to predict and remove the added noise. I wanted to implement that. It was really hard. So I was just like thinking, this is hard, this is expensive, and it's fragile. So what should I do? This, I'm really proud of myself. Actually, this drift trace is going to be a long, smooth signals. When you're thinking about that, it's exactly like the Fourier coefficients, right? Because they are really compact and they're really perfect for, it's a perfect way to, describing the smooth low frequency signals, okay? So I was just like compressing this, drift traces to this, Fourier coefficient, and then I was doing the diffusion on them. It was really easy, okay? And we are training in the coefficient spaces, and then after the training, I was sampling the words in the reverse way. I was just like starting with a pure, noisy, random noisiness. Again, if you were in the tutorial, can you remember that you were working with a really random picture and you were just like taking all of the noises? So I was doing exactly the same thing until I was achieving a realistic drift trace. You should ask me what is the realistic drift trace? I don't know. So I was just like adding some of them that I really know that, but I have to come back to Australia and that's my supervisor. But it still is working perfectly fine. Those items that I know how it works, like the low range and something like that. This one was the result that I got. Both of these methods are random. Okay, so you shouldn't expect to see exactly the same thing. So this is the reason that we have to compare them using the statistic. So I was just like, the left side is just like based on the circuit index, which was 6,000 of them, and this latent angle, and the right side is just like the latent angle and also their density. As you can see, they're just like really bonded, and we have their really slow overlaps, and the marginal of the distribution is really match. I was getting another test to make sure I'm correct. This one. This is just a lag and autocorrection. I just wanted to see how they are acting in a long-range memory. Is it good for the memory? It's going to show the memory and the background memory because it was really important for us. Lag is showing how far apart is circuit index are the two direct values we are comparing. And the autocorrection is going to tell us if I know the control error now, how much can I predict the control error later. What is the lag? If you have circuit I, lag 0 is going to tell you that, and the I is from 0 to 6,000 for my case. Lag 0 is going to tell that how correlated are circuits together with themselves. And lag 10 is going to tell you that how correlated are circuit I with circuit I plus 10. So we want to see the correlation and the memory, right? As you can see that both of them are really great, the hard-coded one and the diffusion one, but the diffusion is better because they decays more slowly and it has a stronger long-range correlation, which is understandable because it's based on the hardware. Diffusion moves the PTNT from a hand-coded control derivative assumption toward a learned latent control noise period. That's it.
Thank you, Fazeleh. Any questions?
I was really stressed.
Yes, sir.
I was just wondering, maybe I missed this. Could you talk a little bit about the physical quantum hardware you're using?
Yes. What is your question?
What was the hardware? What's the QPU, the modality, the type of qubits?
We are just like trying to model the quantum hardware systems, for example, because quantum hardware system has noises, and these noises is coming from the, all of the, controls, or from the background noises. So, yeah.
Okay, it's a simulation-based thing.
Yes, simulations. Yeah.
Any other questions? Yes, sir.
I have a rather primitive question. Is it possible to make these calculations real time, or this is only post-calculation after the quantum computation is done? Does it make sense what I'm asking?
No.
Is it possible to do the error correction real time during the computation is happening?
Mm-hmm.
I'm guessing no.
No, I'm not actually doing that.
I see.
Yeah, but it's a good question. I can think about it, yeah.
Question quantum for me is very difficult, so I don't have the knowledge. But everything you implemented, especially for the noises, I mean, like how to be able to identify these noises, help in identifying it, how that these implementation could be brought to systems that they are already in, instead of simulation in production, how that could be useful actually for the people that are just dealing with quantum system?
Actually, we're talking with several quantum computer companies, and they really wanted to, use our software. This is really important, as I mentioned that, for example, QEC is one of the hot topics in the quantum physics, and people want just like to, because the system has noises and they can't avoid them, they have to find those noises to fix them, right? But the out there software is not, identify all of the noises, because some of them just like ignoring all the noises that is coming from the background, and some noises that other software, some ignoring the noises that's for the controls. So there can't be detect all of the noises that the system has. So even if they are trying to use those software separately, still is not going to characterize the system, because quantum physics is really crazy. For example, if you're just like measuring that, everything is going to vanish. You know what I mean? So you can tell that I'm going to measure everything with one method and again the other method, you know? So you have to do that, both of them at the same time, to be really accurate in characterizing the whole system.
Thank you.
No worries.
Thank you, Fazeleh.
Thank you.